Hmm. All right, now we're on YouTube testing. Testing on YouTube. I feel like it's very quiet. Let's figure out these OBS settings. That's the right microphone. That does seem the right sound level. I think we're good to go. Testing, testing. Yeah, it's just a little bit quiet. All right. How's it going, Kiran Deshmukh? Why is it not starting on X every single time? It says live, but it's not live. How's it going, NLP prompter? You got home in time? Where are you coming back from? All right, I think it's live on X. Let's go ahead and get started. Let me spit out this gum. Take a big sip of water. And today we got the Horn of Gondor for extra support. All right. Welcome everybody to another Hoopo stream. Today's stream is called SmolVLA. We're going back to a little bit more of a classic paper style stream, and we're going to be reviewing this paper right here, SmolVLA, a vision language action model for affordable and efficient robotics, primarily out of Hugging Face, but then a couple different French academic institutions there as well. So I have some slides for this. Initially, I was just going to do the paper stuff, but then I wanted to include other pics and stuff. So you can see the link to these slides in the Hoopo docs. This is on my GitHub. It just has basically all the different docs and scripts and different references that I use for these. So you can see here are the slides, or I should refresh this, and then the slides will be on there. There you go. Slides, if you want to follow along. So SmolVLA is basically Hugging Face's Le Robot. Le Robot is a group within Hugging Face that is focused on open source robotics. And SmolVLA is their kind of answer to the two robotics foundation models that we have available right now. We have Groot N1 from NVIDIA, which was released in their Open Foundation Model for Generalist Humanoid Robots paper. And you can see it's also a vision language action model, which is really just a new terminology that has come to mean basically a vision language model called a VLM with an action expert, which is basically like a little diffusion model that actually produces the action. So it's basically a VLM plus an action expert, and then that has become a VLA, has been the term that has come up to basically refer to these types of models. The other main competitor to SmolVLA is this one here. This is Pi0, a vision language action flow model for general robot control out of physical intelligence. Again, almost kind of identical kind of idea where you take a pre-trained vision language model, you bolt on this action expert, and you get something that can consume images and task descriptions in text and produces actions that you can execute on a variety of different robots. They're mostly focusing on manipulation tasks right now. I would say for things like walking and maybe some of the unit tree demos you see with the flipping and dancing and stuff like that with the Optimus robots, those aren't really VLAs. Those are usually just RL policies that are trained kind of in sim and then shown on the real robot. But VLAs are mostly used for manipulation tasks, which for a long time has really been kind of, there's two separate things there, right? You have kind of locomotion and manipulation, kind of two separate branches of robotics, and eventually they will join. I think in the future they're going to kind of join together, but right now they're still a little bit separate. How's it going? Abranil Chandra and Cal Duz. I wonder if there is a benchmark for VLA kind of models. There is, so they do have some comparisons, and we will be looking at those. So maybe just to kind of, I'm not much of a finance guy, but I think it's interesting to look at the types of companies that are producing these models. So obviously NVIDIA produces and releases open source models because they make money from the hardware. So they're interested in people using they have specialized hardware for robots, right? Like the AGX, the NVIDIA Jetson. These are products specifically intended for robotics use cases. So that's why NVIDIA, it makes sense for them to train models and release them open source. But Hugging Face and Physical Intelligence, this is the money that they've raised. So Physical Intelligence, a little bit newer of a company, right? Started 2024. You could see 70 million, 400 million. So they do have quite a chunk of money in the bank coming from a variety of different investors here. You can see OpenAI investing in them. You got classic venture capital firms like Sequoia. You have famous people like Jeff Bezos. Hugging Face, a little bit older of a company, but a little bit more money. So you can actually see 235, 100 mil, 40 mil. So they've been kind of stacking paper. Hugging Face is probably bigger at this point. More people, more spread out. How's it going, Lil Cam? But this is kind of the order of magnitude of company that is creating these foundation models, right? Because at the end of the day, like to train something like this and have the researchers that could build this and then to just kind of open source it, this is something that is kind of reserved for a certain tier of startup and company, right? But we're going to find out later in the stream that it's actually good for all robotics companies, right? So even if you are in a robotics company that doesn't have this amount of funding and you can't be training and releasing your own foundation models from scratch, I think you're still going to benefit from this kind of competition that we're seeing here between open source robotics foundation models. So we're going to start, we're just going to basically go down the paper here, and we're going to, so obviously there's a little introduction here, related work, blah, 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 but we're going to start with this section here, section 3, SmolVLA. So SmolVLA is a lightweight VLA composed of a compact pre-trained VLM, right? Compact pre-trained VLM just basically means a small vision language model. So in Groot N1, this is their Eagle 2 VLM, which also comes out of NVIDIA. And then in Pi 0, it's Gemma 2.6b, which is like a very small vision language model that's open source that was produced by Google. And a lot of these people on the physical intelligence team are ex-Googlers, so it makes sense that they use the Google open source stack. An action expert trained with flow matching. The action expert is this part right here, right? It's the kind of like tack-on diffusion model that takes the tokens. It's a little bit more complicated than that because it's actually doing kind of cross-attention with some of the features inside the vision language model. But you could think of it like it's basically consuming the kind of semantic information that is coming out of this vision language model, and it's actually producing the instantaneous kind of discrete little actions that you're going to execute on the robot. So that's the action expert. Given multiple images and a language instruction describing the task, the model outputs a chunk of actions. And we're going to kind of explain all these different things. So if you don't really understand what some of these things are referring to, hopefully by the end of this stream, you can get it. Okay. So first we're going to go into the actual vision language model. So that's this part here. The VLM is pre-trained on diverse multimodal data and captures rich world knowledge, right? So they're specifically using SmolVLM2, which is this one here. So you can, all these models are on Hugging Face, and Hugging Face has a nice little kind of UI where you can basically see the model, you can like it, you can follow it, you can look at the organization. There's a community section where you can ask questions. But there's also this part here, which is, I usually find it pretty interesting, but you can see the model size, and you can also see the different types that it's available in, right? So FP32, BF16. BF16 is probably the most common one at this point. But I always find that kind of interesting. So SmolVLM2, also by Hugging Face, and we're going to be looking at the code simultaneously here. So I do have the code pulled up. Let me actually pull it up here. So this is the LaRobot GitHub repo. Inside the common folder, inside the policies folder, you can see a couple different policies that they have available here. You got ACT, you got diffusion, you got Pi0, the Pi0 fast, and now they have SmolVLA. So inside SmolVLA, you can see a couple different files here. You have configuration, modeling, and SmolVLM with expert. The SmolVLM with expert, this is that actually has the model. So this is the actual model right here, SmolVLM with expert. And you can see one of the quargs here that you have to give it is the actual vision language model. So they're using this Hugging Face SmolVLM2 500M video instruct. So probably trained on some kind of video question answering type data set. And then the instruct probably refers to additional post-training step that turns it into that kind of assistant format where you're asking it questions and so on. And you can see here they're loading it with bfloat 16. Okay. So if you actually go into SmolVLM 2.2 base config, here's the config for it. You can see that it actually comes from Idefix 3. So this is the vision language model architecture, or kind of like family, that this particular small vision language model, which forms one part of the vision language expert or vision language action model, is. So Idefix 3 is the kind of model family, I guess you want to call it. There's different sizes, and I think SmolVLM2 is basically just spawns off of that. So another important part of the vision language model is the kind of image encoder. So this is a pre-trained model that consumes the raw images and then produces these kind of image tokens, right? So right here, this little VIT, this is the Pi0 paper, but you can see this image is first going through this little VIT here, which is acting as an image encoder and producing these image tokens. So for SmolVLM2, they're using what's called SIGLIP. And SIGLIP, there's like a million of these, right? So here is a screenshot of Google's Hugging Face page, and you can go on their models and you can see all the different models that they're hosting on Hugging Face. And you can see just how many different SIGLIP models too. So you have SIGLIP 2, 400M, SIGLIP 2 base patch 16, SIGLIP 2 base patch 16, 256 jacks, right? And some of these numbers mean different kind of sizes. For example, the 512, 384, 512, that means the size of the image that's going in, right? So you have some image encoders for bigger images, some image encoders that use smaller images. The patch refers to how many patches are you cutting that image into whenever you feed it into that vision transformer. So based on the SmolVLM 2.2 base config, this is the one I think they're using. SIGLIP SO400M14 364 flash attention to Navit, which is quite a mouthful, but I'm not actually 100% sure. I had there's so many of these, and like I had to dig through these configs, so that might not even be the SIGLIP that they're using for this. Okay. Let's go a little bit deeper here. So in this model architecture, there's a couple different components here. We talked about the vision language model, state action, and feature projection, but we're going to go into this section here, faster inference through layer skipping. Rather than using the last layer features, our action expert has access to all features up to a specified layer n. Okay, so this is something that's very interesting that I think we saw in the NVIDIA group paper. So if you actually look at the NVIDIA group paper, you see how the vision language model here is not just producing these tokens here and then those tokens go into the action expert, right? So that would be the equivalent of using only the last layer of this vision language model. So the first layer would be here, and then the last layer would be here in this diagram, right? It kind of goes this way. But what they're doing is the arrows actually go into multiple parts of the action expert. So This could be the case that they're just taking that last layer and then allowing the action expert to do cross attention with that last layer at various points in this action expert. But I don't entirely remember. But what Hugging Face is doing here is they're specifically taking layers, right, within the LM expert. So you can see here 4-layer IDX in range length of LM expert.layer. So it's going through all the layers in that language model expert. And then they have this self-attention every n layers. And they're basically putting this self-attention every X amount of layers, right? So they're not just using the features, right, at the very top of the vision language model. They're using kind of all the intermediate features and then giving the action expert the ability to pay attention to those intermediate features, right? And the way that deep learning models work is that they have the raw inputs at the beginning, right? The observation, the task description, the robot state. And then as you go deeper and deeper into the model, which in this case, as you go higher and higher up in the layers, right, the features are kind of changing, right? So maybe at the lower level, the features represent kind of more spatial things, like the fact that the table is a table made out of wood, like kind of like more local features. And then as you kind of go higher up in this vision language model, they become less local and more kind of global semantic kind of features, such as, okay, we're picking something up, or like, oh, we're using this type of robot, right? Like, so kind of like higher level stuff. So you want to really give the action expert the most amount of information to make the best possible choice, right? Which in this case is just producing a sequence of actions. So this is a very good idea, where giving the model the ability to attend, right, with this cross attention to multiple levels of this hierarchy of features that the vision language model is producing. Okay, so I think that was a core concept in this paper. Interleaved cross and causal self-attention layers is another kind of highlight here. So the action expert generates action chunks conditioned on the VLM, and the interaction between the VLM and the action expert in VLA employs an interleaved approach where each block contains either a cross-attention or a self-attention layer. So if you see here, you have your self-attention and your cross-attention. Self-attention, and this action expert is a transformer. It's a flow matching transformer. Self-attention means that you're performing the attention computation, right, which is that square, right, where you have the sequence on one edge of the square and then the sequence again on the other edge of the square. And you're basically creating this attention map where every single chunk of that little sequence is paying attention to every other chunk in that sequence. In self-attention, you're doing attention between the sequence and the sequence itself, right? It's like kind of just paying attention to itself. In cross-attention, that means you're doing attention with the sequence, which is coming up from the layer below, but then you're basically doing the attention with some other thing. And in this case, the other thing that you're putting in there is the features from the VLM, right? So alternating that cross attention, right? And you can see exactly here how they do it. Here it is in the code. 4-layer in range num layer. So they're going through every layer of the model here. And if self-attention every n layers and layer IDX mod self-attention every n layer equals 0. So this layer IDX mod, this is basically going to trigger every X amount of layers or n layers, right? And sometimes they're going to put this self-attention, which is forward attention layer, and sometimes they're going to put this cross-attention, right? So they're basically alternating these attention and cross-attention every n layers. And that's how you're getting this very rich signal that's going into the action expert, right? Because this is really where you want the most possible information to make the best possible choice, right? The whole point of this vision language model is almost just to take all this raw observation and just encode it into this like hierarchy of features that can then provide context to the action expert, which is what's actually controlling your robot. Are there any cases where it's really worth getting the extra precision of BF32? I feel like at this point, not really. I think that question is very difficult to answer. That's a question from 770. It's very difficult to answer that question kind of theoretically, right? But much like many questions in deep learning, but I think practically you can answer that question and say no, because pretty much every single model is using BF16, right? So the community has decided, and look at this. This is a future slide, but look at this. NVIDIA Groot, tensor type BF16. LaRobot Pi 0, tensor type F32. SmolVLA base, tensor type F32 BF16. Llama 3.2 11B Vision, tensor type BF16. DeepSeek R1, tensor type BF16, F8, which is even lower than BF16, F32. So you can see that there's still some F32 in there, but it really feels to me like the BF16 is kind of the mode here. And then if anything, I almost see it going the opposite way, right? I feel like we're gonna move into F8. We're gonna actually go down the ladder rather than up the ladder, right? Up the precision ladder would be like into 32 or 64, but I think we're gonna go down into 8, maybe even 4. Lil KM, soon RL in Le Robot. There is actually RL already in Hugging Face. We're going to talk about that, but they do have some reinforcement learning work going on, specifically, for example, the Transformer Reinforcement Learning TRL library from Transformers. But yes, you are correct that this right now is not actually reinforcement learning. This is what's called imitation learning. So I think we're getting there. It's just you got to give them a little bit of time to push it out. Okay. So the next thing we're going to talk about is what is actually going into the model here. So you can see that the input to the model is these 3 images, this task, and then this state. So we can actually see exactly where this is in the code. The VLM process sensory motor states, sometimes also called proprioception, right, which is basically like the joint positions of all the joints in the robots, right? So that's right here, state. See that? Self.prepare state. We're going to see what that does. Images from multiple RGB cameras. That's what this images and image masks is here, self-prepare images. So the model.forward call, that's the actual inference, right? So you can see we're giving it the images, we're giving it the states, and then we're also giving it a language instruction describing the task. And that's this lang tokens, lang mask that's going in here, right? So the natural language that's describing the task is this right here. Grasp the object and put it in the bin. So you can imagine that that goes in and it gets turned into language tokens, and those get fed into the VLM. And you can see that's basically exactly what Groot is as well, right? So Groot receives the images. The VLM is getting those. It's also getting the text tokens here into the VLM, and then the robot state actually goes into the diffusion transformer, the action expert. So I guess it's a little bit different here, right? You can see that in Pi 0, it's also the same, where you're only giving the VLM the images and the text, right? You're giving it the images and the text, and then it's the action expert that receives the previous states, which I think here is also the case, right? Here's the state Q of T, and then it produces the action expert. So I think here the state going into the VLM is actually, I think, slightly different from the competitors. Okay. State action and feature projectors. We use linear projection layers to project the states to match the VLM dimension and project the actions to match the action expert dimension and to adapt the VLM features to align with the action expert's dimension, right? So one of the things that is kind of an issue with these robotics foundation models is that different robots have different state spaces and different action spaces. So what that means is that, for example, a arm that has 7 joints, right? That's what those DOF degrees of freedom mean. An arm might have 7 joints or it might have 8 joints. A dual arm might have 14 joints, right? So the action space is embodiment specific, right? And the observation space or the robot state is also embodiment specific. So you have to kind of adapt that, right? So for example, one thing that they do in the NVIDIA group paper is they actually have a little tiny model here, right? Which is just a little MLP that basically takes the action space and observation or state space of whatever robot you're using and puts it into kind of a more standard format that is the same across embodiments. And that's kind of what people are doing with these projection layers here. So you can see nn.linear. All you're taking is the max action dim, which, by the way, you just pad up until that. So actually, when you get a batch of actions, the first thing you do is you just pad them, which is kind of, you can think of it like adding extra zeros, or like if you have an image that's not perfectly square, you know, sometimes you get those black bars on the image. That's padding, right? So you effectively do that to make sure it's the right size, and then you project it so now it's the correct size to go into the model, right? And these type of projectors, I think in the NVIDIA paper, they specifically talk about they call it here the action encoder and action decoder. These are going to be embodiment specific. So the idea is that you would take this robotic foundation model and you would freeze all of it, and you would allow gradients to go into the state encoder, action decoder, and then you would basically push gradients into those based on your little data set, and that would allow the foundation model to operate your specific robot and understand the actions and states that are coming from your specific robot, right? And the reason you have to do that is because the literal dimension of your observation and action space is different depending on what robot you're using. So that's an important thing to think about. Okay. Let's talk about the action expert. So we were talking about the vision language model, what's going into that. Now let's actually turn our attention to this action expert, which is actually doing all the interesting hard work. So the flow matching action expert, V theta here, is trained to predict an action chunk AT all the way to AT plus N. Okay, so what the hell is an action chunk? Okay, so an action chunk is a sequence of actions, right? So you can see it starts at AT and then goes all the way to AT plus N. So it's like, here's the immediate action, and then here's the action after that, and then here's the action after that, and then all the way to the action plus N time steps, right? So one way to visualize what that is think about AT as being this first dot right here, and then AT plus N as being this dot right here. So basically this is AT plus 1, AT plus 2, AT plus 3, AT plus 4, right? And you can see that the action chunk is basically like this entire kind of like path, right? So you're not just giving it the immediate next action, you're giving it kind of like this little sequence of actions, right? And that's what's called an action chunk, okay? So in all these things, whenever you see this little AT all the way to AT plus H, that is the chunk there. Right, so in this particular diagram, H is the length of that action chunk, but in this formula here, N is the length of that action chunk, right? And across these papers, there isn't like a standardized kind of format or terminology. So like the length of the action chunk, it might be called N in one thing, it might be called, here it's called H in the Groot paper. So you can see that they'll use different variables to define the different parts, but the core thing to understand here is that the action expert is not producing just one action, it's producing this whole chunk of actions. Okay. Crazy to think this, mark with a point here, crazy to think that this type of thing will be on countless devices before long. Yeah, these, not just VLAs, but VLMs, right? I think VLMs on cell phones are going to be absolutely huge, right? The ability to kind of because your cell phone has a camera, right? Like, so using the camera from your cell phone and being able to give you some kind of intelligence that runs on your cell phone, I think is going to be just a huge use case. So the same way that robotics advanced so much because of the advancements in camera technology and battery technology that came with cell phones, I think robotics will also advance because of all the model architecture and model advances that are going to come specifically for cell phones. So it's almost like robotics is getting pulled into the future via the progress that is being made with consumer devices like cell phones, right? So there's not enough kind of robotics revenue to drive research and development, but there's more than enough cell phone revenue to drive the research and development, and then that research and development ends up being useful for robotics. Okay. Let's go back here. So the specific architecture here is a conditional flow matching transformer, okay? And you can get pretty nuanced, right? There's a lot of nuance when it comes to flow matching and rectified flow and diffusion models and all of that, but really you can just think of it as flow matching as kind of a fancy version of diffusion, right? There's a bunch of improvements that have been done in that over time. You can see here's a diagram from, I think, the flow matching paper, where in diffusion, the path that you take in this kind of space to go from noise to the actual, so you're starting here and you're trying to go here, right? You can see it's a kind of a loopy path versus in OT here, which stands for optimal transport, which is, I think, what they're arguing for in flow matching. It goes kind of more straight way. So that wasn't necessarily the best description, but here's a better intuition to have about what exactly is being produced by this action expert V theta, right? V theta is trained to output the vector field. So what is a vector field? So AT tau here, given AT. So given the current action sequence or action chunk AT, right? That's what you're conditioning on. You're producing this AT tau, which is basically the action chunk at the next time step. So what does the time step mean in that? There's a lot of different time steps here. There's the time step from the perspective of the robot, right, which is this AT all the way to T plus N. But then there's a different notion of time, which is the time that you're diffusing in when you're using this flow matching model, right? Because if you guys remember, diffusion models don't work on a single step, right? They're basically this iterative denoising process where you start from noise and then you kind of remove the noise, right? So everybody's familiar and has good intuition for that in image space. And actually, this is actually not entirely correct also, because most of these diffusion models are doing it in latent space. So they're not even diffusing in pure image space like this. They're diffusing in a kind of a latent space. But the core intuition is the same, right? Where you start with noise. So you can see here in the code, the specific part where we're doing this diffusion. We start with a noise chunk, right, that is of batch size, chunk size, and action dim. So max action dim, if you remember, that's the basically how many joints you have in your robot. And then chunk size is the length of this little sequence here, right? And then B size is the batch size, right? So you're producing, or maybe you have multiple observations are getting fed in. In this case, maybe you're doing training, so you're feeding multiple chunks at the same time. I'm overusing the word chunk, but you're starting from that noise, and then here's the actual little loop, right? Here's the actual loop where you're doing these steps here. You start from that noise, and then while time greater than or equal to negative dt over 2, you denoise. So you're basically denoise, and then you're doing this dt times v underscore t. That becomes xt. You go back up to the top, and you denoise again, denoise again, denoise again. So that's what this little while loop is, right? That's this iterative process right here. Okay. So if a diffusion model is iteratively removing noise, how is it actually, what does that mean maybe a little bit more in a more detailed way? What the model's actually producing is a vector field that allows you to remove that noise, that tells you which direction to move to remove that noise. So vector field, whenever somebody says that, this is what you should think of, right? It's a field of vectors where each of these little arrows is a vector. So this is basically saying there's some space for these action chunks, right? And you're starting with pure noise in that kind of action chunk space. How do I move each of those little individual points in this action chunk space such that I move towards the cat image, or in this case, it would be a good action? How do I move from like noise actions to image like actions that are actually good actions, right? And that's the process that you're seeing here in this picture, right? You're seeing basically pure noise, an action chunk of basically just noise, and then at the end of this iterative denoising, you're seeing the nice, clean, denoised action chunk. Here's another kind of diagram of that, right? Where you start, I guess this is like 8 Gaussian. So this is like a randomly sampled points from a Gaussian, right? So you can see that they're kind of centered on that, and then they kind of get more sparse as you go further away from the center. So you could think of this like noise, right? Here's noise coming from 8 different Gaussians, and I think you're trying to predict this blue pattern, right? So you can see how maybe some earlier diffusion models kind of had like kind of a meandering path there. But with these flow matching transformers, you're basically producing these vector fields. You're kind of putting in different inductive biases, different kind of like forcing regularization that makes the path more straight, makes you kind of get there faster, right? Because every single one of these iterative denoising steps is inference, and you want to, inference takes time. You want your model to perform inference quickly, so therefore the less steps you need to do this, the faster your model can perform inference. Therefore, the kind of straighter the vector field leads you to the final answer, the faster you're going to be able to do that. Okay. Are people still following along, or are people like, what the hell is this guy talking about? we're going to go back. There's all of this kind of feeds together. I think as you kind of get more and more of it, you kind of start understanding more and more of it. So we're gonna take a step back. I think we got a little bit deep on the model architecture, and we're gonna talk about another kind of big part of this paper, which I think is secretly kind of the biggest part of this story, is the data, right? And I've said before on many of my streams, I think the data is really the most important part of deep learning and just AI in general. A lot of people over-index on the model architecture because there's kind of like an academic legacy there, right? For decades and decades, the way that you kind of got recognition and citations in academia was mostly through kind of algorithmic novelty and kind of finding some new trick, right? Going from diffusion models to flow matching, right? Like that's where you got all the credit. So a lot of the research community is still very focused on kind of the model architecture. But to me, right, being someone who's a little bit more practical, a little bit more on the kind of like engineering, kind of prototypey kind of side of it, it's like the data is by far the most important part, right? So unfortunately, you don't get a lot of credit for cleaning data sets and finding new data sets, but I think in terms of actually producing the highest quality model, I think the data is pretty much the most important part. So I think Hugging Face really did a good job here, and here's their strategy. So open source data contributions collected by individual practitioners enable the larger robotics community with community datasets. Datasets collected in diverse real-world settings from academic labs to homes as part of a larger effort to decentralize and scale robot learning with open source. We select a subset of 481 community datasets obtained from Hugging Face, filtered according to embodiment type, episode count, overall data quality, and frame coverage. Okay, so what does this mean? So the robot, the way that they kind of strategized their goal is that one of the first things that they put a ton of effort into was this idea of data sets, right? So if you actually, what is a data set in this case? In this case, a data set is a bunch of episodes. So you can see here you have episode 1 all the way to episode 50. And in this case, it's SO100 sorting. So they're taking this little SO100 robot, and this is probably someone teleoping it, right? So off the screen, there's some guy holding another version of this little robot and kind of like grabbing this blue block and then putting it in that thing, right? And you can see here are the each of the different joints. So the action space for this SO100, right, has a certain amount of joints, and then for each of those little joints, that's what every single one of these joints is doing at every single time step. And here's the camera from the what's called the overhead or the top view, right, which is a camera that's kind of looking at the whole robot, and then you have the observation of the actual camera on the wrist. And the reason you do this is actually because the wrist camera, being very close, has a lot of good context about the kind of actual manipulation and the contact that might be occurring between your gripper and the object, but it's also shaky, right? So the wrist camera has a lot of like blur and is shaky. The overhead camera gives you the more kind of global context of like, okay, what is this scene? What robot am I using? Like, what are the objects that are available to me? So having both of these image inputs is important in robots. And you see pretty much all of these papers doing that, right? So I guess here for the Groot N1, they don't have an overhead camera. You just have the head coming from the humanoid, or the camera coming from the humanoid head. So that's just one image there. But for example, here in the Pi Zero, you can see how they have the overhead image, and then they have the gripper cam on the left and the gripper cam on the right. I think most people call these wrist cams now, but wrist cam, gripper cam, basically the camera that's like right there looking at the actual grasp. And I think that's something that's going to explode as well, right? Kind of going back to what we were talking about with the cell phone cameras. I think cell phone cameras are so cheap that it might be the case that we'll see robots that have like 100 cameras on them, right? I think right now a robot might have up to 10 cameras, right? We're on the order of magnitude of like 1 to 10. But imagine if you had a camera on your elbow, right? And you had a camera on your shoulder, and you had 2 cameras on your wrist. You had a camera on the back of your wrist. You had a camera on your palm. You had a camera. See, the more cameras you have, the more kind of context you can provide, the more information you have available for these models to make the right choice. And I think that because cameras are cheap, I feel like we're going to get to the point where we have hundreds of cameras on a robot. I don't know if we'll ever get to the point that we have 1,000 cameras on a robot. That seems a little bit too much, but to me, like 100 is the right order of magnitude. Okay. Let's go back to this. So Hugging Face, right, spent a lot of time creating basically this Le Robot dataset format, right? And they have these dataset visualizations. So they're basically trying to standardize the dataset format. And Hugging Face already has all this infrastructure for kind of posting datasets. And you can see here, look at all these datasets, right? So these are all different datasets that people have collected that are all in the same format, which is basically a gold mine, right? And not only that, but a lot of these are using the same exact embodiment, right? This SO100 robot. So Hugging Face has a very clever strategy here, and you can actually see them kind of leaning into it with these events. So they keep hosting these kind of like hackathon events. And because these robots are so cheap, they can just buy like 10 of these robots and then put them there at the event, and then they get a bunch of random people to come, and they basically create some little data set for some little task. And what is the end result of that? Well, the end result of that is, one, not only do you have now more kind of people that are interested in this robotics task, but now you have a bunch of little community data sets. So Hugging Face has figured out a way to use the community to collect a large data set for a specific robot embodiment that's all in a unified format, and that's all available kind of easily. You can download these very easy, right? Because these are all kind of in the cloud like this. You can, let's say you're using some cloud GPU to train, it's very easy to download these data sets from Hugging Face with a Hugging Face key. So I think the data strategy that Hugging Face has for open source robotics is very, very intelligent to me. I think it's a very good idea to use the community to kind of outsource data set collection. Okay. 770. I'm still confused as to how different robots with different degrees of freedom are supposed to be able to work with the same model. So right now they don't. So if you took this model, right, which has only ever seen the SO100 robot embodiment, right, and you just try to put in a robot. Let's say that it had the same degrees of freedom. So let's say it was literally the size of the action vector is the same, but the joints are different, right? So maybe in your robot, the first joint has like a slightly different rotation than the joint in the SO100. It would not work, right? These robot foundation models, they are embodiment specific. You have to fine tune them to your specific embodiment. So whenever you're fine-tuning the model, right, you don't really need to fine-tune the VLM and you don't want to be pushing gradients into this whole system here, right? What you really want to do is just push gradients into these little action encoders and state encoders. So that's, I think, the strategy that you're going to see with these robotics foundation models, is that they're not, in order to be able to use this model on a variety of different robots, you're going to end up in a place where you have to collect a fine-tuning data set, and then you're going to basically fine-tune specific subcomponents within this model so that it works on your specific robot. Okay. So we were talking about the data set story and using the community to kind of collect these data sets. Here's another big part of the story, and I think people are sleeping on this one. I think this is one of the more interesting kind of threads in robotics right now, is this idea of vision language models, not as a part of the VLA, but like as a kind of a task annotator or a success detector. So we observed substantial noise in task annotations, natural language descriptions of the robot's intended behavior for a given data set. So what happened is that whenever they made these hackathons, right, and they just had all these people creating these data sets like this one, SVLA SO100 pick and place, right? At some point, some human had to basically decide what the text was for this, right? So some random human sat there and then typed in, this is going to be grasp the object and put it in the bin, right? So if we go back to our visualizer, where's the visualizer? I think I accidentally clicked out of it. Yeah, so someone decided, I don't even know how to get the text description for this, But somewhere in this view, there's the text description. Those text descriptions are very noisy, right? So how are you gonna clean those? How are you gonna clean like hundreds of noisy test or task descriptions? Well, one thing you can do is you can feed images from that task or from that specific data set into an off-the-shelf vision language model. So to improve the annotation quality, we use an off-the-shelf vision language model, Qwen 2.5 VL3B Instruct, to auto-generate concise task descriptions. Okay, so what does that mean? That means that kind of similar to, if you remember when we were reading image generation model papers, right? They were talking about taking the image captions, which are usually kind of not particularly great, and augmenting them with a VLM, right? So they would take an image that was captioned with like a giraffe, and then they would use a vision language model to turn it into something more descriptive, like a tall giraffe reaching over the bush and eating the bush or something like that, right? And that the more text tokens you have on that description, the better, the more kind of information there's going to be whenever you're doing, for example, the cross attention inside your VLM between the image tokens and the text tokens, right? So you want rich descriptive task descriptions, and it's kind of, we're in a weird place where suddenly we have the perfect, it's like we need rich descriptions, and we just happen to have created a technology called vision language models that have this exact type of kind of semantic-y, kind of high-level world knowledge that's perfect for this. And going beyond this, I think, to me, VLMs are not just revolutionizing robotics because they're part of the VLA, but because they're also kind of solving these secondary problems, right? So here's a paper called Vision Language Models are In-Context Value Learners. And in this paper, they're also using VLMs for something slightly different, but similar, where you can say, okay, well, I have huge amounts of data set. How am I going to filter these for high-quality ones? How am I going to detect success, right? Say I have my robot kind of gathering data. I want to know exactly the frame whenever it actually succeeded, right? Was this a success? Was that not a success? So we're seeing kind of a very important use here with vision language models as kind of a reward function, if you want to think of it that way, but they're providing the actual signal that you are then using to improve the dataset quality, which then improves your robotic foundation model. So keep paying attention to this, the use of vision language models as these kind of like for dataset filtering, success detection, kind of reward. I think in this paper they actually use it for progress. So it's like they have like a, how far along are you in folding the t-shirt? Are you like 80% of the way done folding the t-shirt? Are you 100% or 40% done folding the t-shirt? And I think the combination of VLMs for feedback and then simulation, because you could use a VLM for feedback in simulation, right? You could give a VLM an image of a simulation and say, hey, did I successfully put the ball in the cup in this simulation? And the VLM can say, yeah, you did. Or it can say, no, you didn't. And then now you can start doing a bunch of tasks in simulation where the reward criteria is a little bit more fuzzy, right? Because up until now, if you wanted to do a task in simulation, the reward criteria needed to be explicitly defined by some human, right? So like maybe you're doing some kind of standing up task in simulation, right? Someone's actually coded something where it looks at the center of mass of the robot and it says, okay, is the center of mass of the robot above this particular height? Then it's a success, right? So rather than using those kind of hard-coded reward criteria, you're now seeing the use of vision language models, more kind of like fuzzy reward criteria. But because it's, I think, more powerful, it's like fuzzy but in a more powerful way, I feel like there's going to be a lot of improvement just simply from that. Does OpenAI Operator use a similar model like a VLA? Probably. I don't think so you're talking about basically models that use the computer, right? Operator is an OpenAI model that basically clicks on stuff for you. I don't think they need this diffusion transformer, right? So if I had to guess what the OpenAI Operator model is, it's just a vision language model that has additional tokens, right? So it's a vision language model where they've added extra tokens such as click on the screen, move cursor to this location. So they've added action tokens, right? Tokens that produce a certain action on the screen, right? With a robot, you can't just use action tokens because you actually need to produce this the actual kind of continuous actions in something like a joint space, right? So this is a Cartesian space actions, right? But those are a continuous space. That's why you use these action experts. But for a model that's just operating your computer, you don't really need this action component. You can probably use a vision language model that just has action tokens, and it simplifies it for you. That's my guess, but I also don't work at OpenAI, so I don't actually know if they're doing that. That would be my guess, though. Good question, SHZ. Okay. So we were talking about VLMs, and then I just wanted to bring this up because this is something that I heard in the most recent Dwarkesh podcast where he talks to these two Anthropic researchers, and one of them talks about the situation where he's like, the really scary future is one where AI can do everything except for physical robotic tasks, some robot overlord telling humans what to do through AirPods and glasses. So he's imagining this future where you're wearing like augmented reality glasses, and there's an AI that is looking at the feed coming from your augmented reality glasses and telling you, hey, grab the blue thing and put it in the purple bin. And then you as the human are like grabbing the blue thing and putting it in the purple bin. But this is wrong, right? And this intuition is actually completely bullshit, because if you have a vision language model that is good enough to give that kind of feedback, then that vision language model is good enough to provide a reward signal for a robot, which means the robotics is also solved. So I don't feel like there's ever going to be a future where vision language models are smart enough to give you that kind of like immediate feedback, but somehow robots are not possible, right? I think if you solve that problem, if you get vision language models to that level of fidelity, then you kind of in a way solved robotics. And one piece of evidence that I have to kind of show that is a classic robotics video. This is from 16 years ago called PR1 Robot Tidying Up a Room. So this was one of the very early demos of teleoperation. And in this case, you had this bimanual robot that was being teleoperated by a human, and the human was able to basically perform all these different tasks, like putting all the dishes in, taking all the dishes out, all of that entirely teleoperated. So I think people who are not in robotics think that manipulation and robotics is hard because like the hardware is difficult and like something like they're just afraid of like the idea of like contact and like manipulation, but that's not actually why it's hard. The reason why it's hard is because like we haven't had the ability to be very, very to have these kind of fuzzy rewards and kind of fuzzy feedback, right? But now with vision language models, we have the ability to do that, right? We have the ability to kind of give this fuzzy feedback. So I feel like we're very close to solving robotics in that sense, right? Because of VLAs. Okay. I just wanted to point that out, that I don't think you're going to be packing Amazon bags in a dystopian future. I think if the VLMs can give you feedback on how to box an Amazon thing, robots are going to be able to do it. Please volume up your microphone. I'm going to yell more. It's already max volume, guys. I don't know what to do. Look at that. I mean, it shows me the yellow, so that should be right. Okay. I'll talk a little bit louder. All right. Another big part of this paper that I want to talk about here is asynchronous inference. So here we have a whole section devoted to this. But it's an important part. So asynchronous inference. The model outputs action chunks, right? So our model, pi, takes in O of t and produces A of t, right? Which we already kind of talked about, the fact that the model is taking in some observation, which is our images and our task description and our robot state, and it's producing this chunk of actions, at all the way to t plus n, right? From the environment observation O of t. So now, how do you actually execute that, right? So in order to do this, we're going to take a little step backwards and talk about ACT. So this is the original ACT paper. So actually, if you remember when we were looking at the code here, right? So one of the policies here that the robot has is this ACT, right? Action Chunking Transformer. And this is kind of one of the most popular robot policies, although now that we have these foundation models, ACT's going to kind of die off. But this was one of the kind of foundational works in modern robotics. And there's a lot of interesting things in this paper, right? The hardware was very nice, the arms, the demo was super awesome, but the ACT, right, a core chunk of that name is the action chunking part. And what does action chunking mean, right? So you're getting back these chunks of action. So your model. All right, I think we died there for a second. Testing, testing. I'm back? Okay. Back? All right. Okay, so we're talking about the action chunking, right? So let's say you send your observation to your model, right? You give that model pi O of t, and actually you can see the model. You see how they're representing it as a function with pi? That's why physical intelligence uses pi as their logo, right? Because it's kind of like they're the model, right? So pi 0 is the first model, right? So that's kind of where their name comes from. But okay, you're feeding your observation O of t into your model, and it's producing this action chunk, right? You could just execute that, and then once you're done, you feed another observation, get another action chunk, and then go through that again, right? So that's one thing you could do. Let me double check here, because I feel like I'm not actually live. Okay, we are live. It's just my YouTube studio view is not, whoa. Okay, but here's the problem, is that by the time you execute this green action, right, the observation you're using to execute this green action was from over here. So it's like kind of outdated, right? So you don't really want to execute this entire chunk here. In this case, it doesn't matter because this brick isn't moving. Nothing in the scene is moving at all, right? But in a more kind of live situation where there's stuff changing, you want to be a little bit more reactive, right? You don't want to just execute this entire action chunk. So what the ACT paper introduced was this idea of kind of temporal ensembling, where you get the whole action chunk back, but then you don't necessarily execute that action specifically all the way until the end and then get the next action chunk and execute that. What you do is that you're constantly sending these observations at every time step, and that's producing an action chunk. So then you're taking all these action chunks that are coming back, and at any individual moment in time, you're actually, the action that you're actually executing on the robot is this kind of ensembled action of all the previous actions, right? So at time step 1, you're not executing the second action from the first chunk. You're executing this kind of blended combination of the second action from the first chunk, right, and the current action from the chunk that you just sent, right? And then at time step 2 on the robot, you're executing this blend of the action, the third action from the first chunk, the second action from the second chunk, and then the 0th action from the current chunk, right? So what does that mean? That means that your robot is kind of more smooth, right? Because if you have any situation where you suddenly give it an observation and the model produces something weird, well, that weirdness is only going to be limited to one chunk, and because you're executing these kind of like chunk blends, right, it's going to be more smooth. But it also is more reactive, right? So like let's say if in between time step 2 and time step 3, you suddenly put your hand in front of the robot, right? This red chunk here is going to suddenly say stop. So now you have stop and then go, go, go. But now the robot's going to kind of pause because it was able to react quickly, right? So this idea of kind of temporal ensembling of the action chunks is, I think, a very good solution that I don't think ACT was necessarily the first to really introduce this concept. I'm sure someone could pull a Schmidt-Huber and dig up some 1980s robotics paper where people do this, but this was really the popularization of this idea of action chunking and then this kind of ensembling or kind of blending of actions to produce a kind of smoother, more reactive robotic control loop. Okay. So Hugging Face in their VLA, SmolVLA, kind of has their own version of this, their own kind of terminology around that. where they interleave chunk predictions, right? The chunks that come out of one individual observation, and chunk consumption, computing a new chunk of actions at every time step and aggregating the predicted chunks on overlapping sections, which is basically what's going on here, right? So what they call this is they call this synchronous inference versus asynchronous inference, right? So in synchronous inference, it's basically what's happening here, right? You send the observation, you get the chunk, you execute the chunk, and then you stop, you get another observation, you send it, and so on. Actually, let's use this one because this is the one that they use. But in async inference, you're kind of already performing actions as you're sending and waiting for the chunk to get inferenced on the policy server. So let's go into, this is a little bit of a confusing figure, but if you can understand this, I think you'll be in a very good place to understand exactly what action chunking and asynchronous inference is. So there's two things here. There's what's called the robot client, and then there's what's called the policy server, right? So what does that mean? So what that means is that there's actually two different computers here, right? So here's a screenshot from my robot that I've showed before. This is what I call TatBot. I'm working on a tattoo robot. You can follow the journey on my X and various accounts that I've posted here. But on this machine, I actually have two different computers. I have a System 76 Meerkat, which is basically just a CPU, and then I have the NVIDIA AGX Orin, which is it is a GPU basically, right? So it's a kind of a edge GPU, right? So it has a unified memory, but why do I have these two computers? Well, I have these two computers because the System 76 Meerkat, which has the CPU, that's what's actually connected to the robots, right? So that's what's actually sending direct, telling the robots to actually execute actions, right? So in this diagram, it is the robot client, right? The AGX Orin, which is the GPU machine, that's what's actually holding the model, right? That little VLA model, and it's what's actually performing the inference, right? So in this case, that's what's called the policy server, right? So the machine that's directly connected to the robots, and then the machine with the GPU that is actually holding the model and doing the inference on the model, right? So that's the robot client versus the policy server, right? So the robot client, which is actually connected to the robot, is receiving the observation, right? Which is the current state of the robot and maybe the images and so on, right? It then packages that up, right? And then sends it to the policy server. The policy server, which has the actual model, will then feed that into the model and then produce some action, right? Receive n actions from pi given that observation. Now you have that action chunk. So right at this point, right, the robot client has now received a fresh little action chunk, right? So it's sitting right here. It sent the observation. It got back this nice little action chunk. Okay. Now what is it going to do? Well, it's going to perform these actions, perform the action, perform the action, perform the action, and then it's going to take an observation after some k amount of time and then send that chunk back up, or send the observation back to the policy server, and the policy server is going to then do the same thing, right? It's going to take that observation, it's going to feed it through the model, and it's going to produce some action chunk, right? But there's some notion of latency here, right? Where there's actually the latency that it takes, so the model isn't going to instantly produce action chunks given an observation, right? It takes some amount of time for this little AGX Orin to receive those observations and then output those action chunks, and that's what's called the inference latency here. But it actually is more complicated than that, because there's actually the time to send the observation between the client and the policy server, the inference latency of the policy server itself, and then the time to send the action back from the policy server to the robot client, right? So it's important to remember that robot client and policy server, these are two different computers, right, connected via Ethernet. So anytime you send stuff over Ethernet, there's this kind of like packaging and unpackaging process, right? Serialization, deserialization, right? You have to take that observation, package it up nicely into a little message that can be sent over the Ethernet to the policy server. Then when the policy server gets it, it has to unpackage it into a little message that it can feed into the model, right? And that type of packaging, unpackaging, like the network protocols, people have been optimizing those for like decades and decades and decades. So they're pretty fast and they're pretty efficient, but they're not negligible, right? So there's the overhead of actually sending it, and then there's the actual inference latency, right? But what you really should be thinking about here is that there's kind of an asynchronous nature to this, right? Where by the time you're actually receiving these observation or the action chunk that is coming from your policy server, it's now been some time since you sent that, right? So you actually got that observation here, but you're not actually executing the actions until here. So there's this kind of asynchronous nature to it, right? Where you're sending in an observation, it's taking some time to get you the action chunk, and in the meantime, you're going to execute this weird blended combination of previous action chunks. And that is what they call asynchronous inference, which triggers chunk prediction while the control loop is still consuming previously available chunks, aggregating it with the newly coming chunks that are coming in from the policy server. So this decouples action prediction from action execution, which is very, very crucial, right? Because now you're no longer sitting there and your robot would be waiting, right? If you didn't do this, your robot in between sending the observation and receiving the actions would just be sitting there. It would just be sitting there completely still, waiting for the chunks to come in so it could execute the next chunks, right? So you're saving that amount of time by doing this asynchronous action execution with two different computers like this. And I suppose you could do it on the same computer if you really wanted to, but separating it out so you have like a very good CPU computer like the System 76, and then you have a very good kind of GPU computer like the NVIDIA AGX Origin. Separating that out, I think, is going to be a very common design pattern, right? And it's something that we see in other robot companies. So here, for example, is a couple images from the blog post that Figure had. So Figure is probably one of the more well-funded robotic humanoid startups, right? They're kind of a Optimus, you could think of it that way, Optimus competitor. But they introduced this Helix, which is a very similar kind of idea, right, to these VLAs, right, where you're basically using a vision language model, which has all that kind of rich world kind of semantic knowledge, and then this kind of action expert, this kind of diffusion model type of thing, which produces these kind of continuous actions, right? A continuous chunk of actions, which you then execute. But, right, they call it System 2, which is the infrequent vision language semantic reasoning, and then System 1, which is a fast reactive control. This is the 80 million diffusion transformer. This is the 7B vision language model, right? And they actually make the distinction that, hey, actually, the vision language model, the inference time for that, right? So the inference time here is actually much larger than the inference time of the action expert, right? This little tiny flow matching diffusion model, that inference is going to be faster than the inference of the vision language model. So actually, they separate it out. They basically have, they make the distinction of, okay, System 1 or the action expert is fast, System 2 or the VLM is slow. And that's kind of why the kind of highlight that they were having. But the thing I wanted to talk about here is this little sentence here. Figure robots, each equipped with dual low power consumption embedded GPUs. So every single one of these robots has 2 GPUs in it, 2 GPUs. So it's a pattern that we're starting to see here, where all these robots, we're starting to just put 2 different edge devices on them, right? So I have 2 edge devices on my robot. Figure has 2 edge devices on their robots. And then actually, if you go back, even Tesla does this as well. So Tesla, the FSD computer, which is the full self-driving computer, which is the computer that's in a Tesla car that actually allows it to be an autonomous vehicle, is also a dual computer. So they are using it more from a perspective of redundancy. So I think the reason they have 2 different system on a chip here, so 2 different computers here, is because in an autonomous vehicle, you really don't want the GPU to fail, so having 2 different GPUs allows you to have a little bit of safety there. In this case, we're seeing it for a separation of System 2 and System 1 because System 2 is going to be slower than System 1. And then in my case, we're seeing a separation for the fact that you can do this kind of asynchronous inference. So I think I'm seeing a pattern here where it's very likely that we have separate compute within a robot. I tried to join the Discord community, but the link expired. I appreciate that. Thank you. I will try to update the link. If we want instant motor reaction, we should make motor and visual into one multimodal thing. Yeah, I mean, that's kind of what's happening with these vision language action models, right? But it's a trade-off, right? The reactivity is basically a trade-off between the inference, right? Because ultimately, you still have to wait for the model to perform the inference, right? So if you have this really big model, it's going to take a long time to do the inference, which means the robot isn't going to be as reactive, right? So executing action chunks and blending those action chunks in an asynchronous way with a policy server that is doing the inference on the model, that's going to give you this blend of reactivity and performance. Okay. One more thing here on the action chunking is this interesting figure 3 here. So in the paper, figure 3, they talk about 3 different kind of situations with this asynchronous inference. So in this first one, right, and on the x-axis here, we have inference time steps, and then on the y-axis, we have the action queue size. So the action queue size, you can kind of think of it like the length of this here. So it's kind of like how many actions do you have queued up, right? So in this case, we have 4 actions, right? Or you can think of it like the chunk of the length of this, right? So how many individual little actions do you have queued up? It's not necessarily, it's not exactly that, but that's the right intuition. So in the first example here, the client drains the entire chunk before forwarding a new observation to the server. So in this case, right, the robot is sending the observation to the policy server. It's receiving a chunk, right? So now it has 20 little actions that it can execute, and it's executing every single one of those actions before it gets back down to like, I don't have any actions to execute. I don't know what to do. I'm going to record an observation. I'm going to send it back up to the policy server. And then I'm going to get a chunk of actions, and I'm going to execute all those chunks, right? So that's what's happening in this first one here, right? It's this kind of like synchronous format where you're sending the observation, getting a chunk of action, executing all those actions. Getting the next observation, sending it to the policy server, getting the chunk of actions, executing all those actions. This one here, G equals 0.7, is asynchronous inference. This is where you allow the client to consume a fraction of a queue before triggering inference. The overlap between successive chunks provides a buffer against modeling error. So now you're getting an observation, sending it to the policy server. The policy server is giving you a chunk of actions, and you're executing those actions. But before you can even finish executing all those actions, you're taking another observation and sending that to the policy server again, which is giving you a chunk of action. So this is kind of more like this one here, right? Where before you've even finished executing these chunks, you're already receiving the next chunk. So you're kind of now executing these blended chunks or overlap between successive chunks. And here they call it a buffer against modeling errors, which is kind of a fancy way of saying that, okay, when you execute these kind of blended actions from multiple different chunks, if your model had any kind of weirdness in it, right, that weirdness wouldn't impact the robot so drastically because it's now being blended in with previous chunks, which are less likely to have that weirdness, right? So it kind of gives you this kind of more smooth or a buffer against modeling errors, right? And then here's the compute intensive limit. And this is the last plot here. So in this extreme case, an observation is sent at every time step, right? So you're now sending an observation immediately at every single time step. And this is what Zhao et al., which is that ACT paper. So in this ACT paper, here's Tony Zhao, who I think is this guy here, actually controlling the robots. But here, you're actually sending an observation every single time step, right? So you're getting an action chunk at every single time step, and that's what you're seeing here, right? Where it's basically you send the observation, get an action chunk, and then even after just one execution of one action inside that action chunk, you're immediately going and getting another chunk back and blending it in. So you can see how it's basically just like throttling at the very high part of the action queue size here, because you're constantly receiving action chunks because you're constantly sending observations. So while maximally reactive, right, because you're immediately getting feedback from the model, this setting incurs one forward pass per control tick and can prove prohibitively expensive on limited hardware, right? So what they're saying is that, hey, this kind of extreme case where you're constantly sending actions, to the model means that your policy server is constantly executing inference, right? And when you're doing that, you're taxing your GPU, right? And let's now imagine a future where the GPU is not actually on the robot, the GPU is in the cloud, right? So if the GPU is in the cloud and it's performing inference for hundreds of robots, you might not want every single robot at every single action to give you an observation, and then now you have hundreds of robots giving you observations at the fastest possible control loop, right? So there's this kind of trade-off that we're going to see, especially whenever you have a shared policy server that is performing policy inference for a variety of different robots. You're going to see this kind of trade-off where, okay, how often are you getting an action chunk back and sending an observation? And one thing to kind of bring up specifically on that is maybe something a little bit creepy, but are we going to see a future where the policy server is attached to the robot like I have here, right? Or where the policy server is inside the robot like Figure has it? Or are we more likely to see a future where the robot only has the kind of robot client, right? It's just a very small machine with just a CPU that's just executing action chunks, and then the policy server is in the cloud, right? Because, one second, I'm going to cough here. Because here's the real secret, is that cloud inference means less compute on the robot, which means a cheaper robot, which means no privacy, right? So if this NVIDIA AGX Orin is like $2,000, right? That's one of the more expensive components of this entire robot. If I can get rid of that NVIDIA AGX Orin, my robot just now got significantly cheaper, right? So more people will buy my robot, right? If Figure took out one of the two GPUs in there, there'd be a cheaper robot. And it's fine. Hey, we can have a big cloud and we can have these big machines in the cloud that are serving our policy and that are doing batched inference. It can be very cheap. We can kind of control the amount of observations that we're getting per robot, and we get your data, right? Because if we're now doing the policy server in the cloud, that means your data is leaving your house, going to the cloud where it can be stored, it can be searched through, it can be filtered, the FBI can get it, the CIA can get it, you know, they can do whatever they want with it, they can request it from the person, or they can go to the company and be like, hey, give us the full video data from the home robot of this user, right? So I just feel like there's kind of a very bad alignment of incentives here where cloud inference for robot policies allows the robot to be cheaper, and it also gives the big corp your data. So I don't know. I'm not particularly thrilled about it, but it could be that we move into a future where basically the robots don't have an edge GPU. They basically can't do any inference locally. They just have a very, very cheap machine that is just doing this robot client type of work, and then all the kind of inference, all your data is leaving so that it can the inference can be performed in the cloud. Okay. So with that, let's now go. We're almost done here. We're going to go into the next section in the paper, which is experiments. Okay. So all the experiments on this paper are mostly done on these SO100 and SO101 arms, which are these super cheap arms that Le Robot is all about, right? So in pretty much all their hackathons, it's all using these little tiny arms. And they're kind of toy arms. You know, you really can't do anything like useful with these arms, but because they're so cheap, it's better to get a lot of people to use them, right? It's easier to create a decentralized community of open source robotics that are all using the same embodiment if you make that embodiment very cheap and easy to 3D print. So I can understand why Hugging Face is going that way. We'll skip that for now. Let's go into here. Baselines. So they're going to be comparing their model against two popular and strong baselines, ACT, which is from this paper, right? Action Chunking Transformer, and then Pi0, which is the
VLA from physical intelligence. So Pi0 is a 3.3 billion parameter VLA, again, very tiny, with 10,000 hours of cross-embodiment robotics data. And then ACT is a little bit dated at this point, a conditional variational autoencoder with 80 million parameters, and ACT is generally trained from scratch for some specific use case. And you can see here real-world benchmarks. So we're now comparing ACT, Pi0, and SmolVLA. So kind of a weird situation here where in pick and place, Pi0 is getting 100% success, which is extremely impressive. SmolVLA gets 75, but then for stacking and sorting, you get higher in SmolVLA than Pi0. So kind of an interesting situation there, right? Where you can see how, to me, what this is telling me is this is a story of the data sets, right? So SmolVLA is trained on these kind of like hackathon community data sets versus Pi0, right? They have in-house people that collect all their data for them. So the Pi0 robot, I think the data set that is used to train that is more narrow, but it's more focused on the specific application of picking, which is why it gets such a high pick and place score, success rate. But because the SmolVLA has a wider variety of different tasks, right? The diversity or the variance of that SmolVLA data set, because it's a decentralized community data set, I think that's what makes it better, kind of a wide variety of tasks. So whenever you start evaluating it based on the average performance at a bunch of different tasks, right, kind of like an aggregate benchmark, you get a higher score than Pi0. So obviously this is their paper. They're going to kind of come up with some benchmark where they're the best, but I thought it was interesting that they beat Pi0 by going wide, right? Rather than saying, hey, we're gonna beat Pi0 at pick and place, they're like, no, we're gonna have a bunch of different tasks and then show that our performance on these tasks in aggregate is better than the performance of Pi0 on any individual task. Okay. Success rate, I think this is exactly kind of what I was saying, where effective pre-training and multitask learning. So in here, VLA PT, this means VLA pre-training. So they take the same VLA model, the SmolVLA, and they say, okay, train with a single task versus train with multiple tasks, and then train with multiple tasks and also include pre-training, right? Which is where you give kind of more generic, potentially not even robotics, kind of like vision question answering to the vision language model, right? And you can see here how it improves performance. And this isn't surprising, right? Like I think anybody in deep learning can kind of guess that this was going to be the case, but this is just another data point for larger data, more varied data being an important source of performance, right? Where we see here in this figure from the Groot N1 paper, in the Groot N1, they have this kind of data pyramid where they say, okay, you start with the internet, right? The most generic data, and then you start specializing. Then you have synthetic robot data for all embodiments, and then you have real-world data for specific embodiments, and then at some point you have real-world examples of your specific embodiment. That's like the final thing that you train on, right? But this idea of kind of a data pyramid where you have a ton of data at the very bottom, and then you kind of get more specific as you go up top, that just seems like the winning recipe to me. Let me see here. Okay. Let's go here. Expert width. So adjusting the expert's hidden size affects performance. Larger capacities yield better success rate. So this is success rate on Libero, which is this here, a benchmark for lifelong robot learning. You can see it just kind of seems to be a bunch of manipulation tasks with a Franca arm. But here they're talking about expert width. And sometimes people get confused about width and depth. So whenever you have a deep learning model, the depth is like kind of how many layers there are, right? So this would be a deeper model. The width is how wide the individual layers are, right? So the hidden size is basically the length of this here. So making an expert wider means you're basically increasing the number of neurons kind of in the width dimension. And what you're doing there, right? If you think about it, what does this layer mean? Well, the layer, each of these neurons is going to have some kind of number, some kind of activation, and that you can think of it as a vector in some high dimensional space, right? So in a three-dimensional space, right, you're trying to build this feature manifold that exists in that three-dimensional space. If you increase the amount of dimensions, now you have a five-dimensional space, you can have a much more complicated, there's a lot more space to put your features in there, right, to build this rich feature landscape, right? So the wider you make a model, the more nuanced and intricate and the more information it can hold in each of the layers. So basically, what kind of what people call this is model capacity, which is kind of like how much space is there to create rich and interesting representations within the model. And here they show you how if we take the width of the VLA, right, and we make it 1/4 the width versus the full width, we can see a direct difference in the success rate, which again is kind of similar to the pre-training figure here, where obviously we knew that pre-training was going to help, and obviously we knew that increasing the width was going to help, but it's always good to kind of see data points that confirm our intuitions. So wider models are better, more varied data is better. Okay. And okay, the next thing I want to talk about here, especially right after we talked about expert capacity, is that we're still very, very early, right? So all these VLAs, right, whether it's Groot, whether it's the Pi Zero, whether it's SmolVLA, these are all still very, very small, right? So here we have NVIDIA Groot, 2.19B parameters. Le Robot Pi Zero, 3.5B parameters. SmolVLA Base, 450M parameters. So these are all tiny, right? Like compare this to Llama 3.2 Vision, which is just kind of like a generic vision language model, 10B parameters. It's an order of magnitude more. The most recent DeepSeek R1, 685B parameters, right? Multiple orders of magnitude more, right? So why are we using all these tiny ass little models? Well, the reason we're using tiny models is because they need to fit on this tiny little NVIDIA HEX Orin, right? They need to fit on this low power embedded GPU. So right now, robotics foundation models are very small because they need to fit on these edge devices. But if we move into a future where the policy inference is happening in the cloud, why not use a big, giant 685B parameter model? So I think there's still a couple big unlocks in the performance and generality of these robotics foundation models that we can get just with increasing the scale of these models, right? It's like we still haven't even gotten to the point where we're kind of at the limit of what we can fit on a GPU, right? So robotic foundation models, some people are like, they barely work, like they're not even doing that much, they're very specific, like these are kind of trash. And it's like, okay, they're not particularly great, but like they're tiny, right? Like, like there's still so much room to grow here. Okay. Here's another thing, another kind of improvement. So this is now, we're deep in the paper, we're past the experiment section, and we're now into the discussion section. So in the discussion section, they have this limitation section where they talk about all the different things that they can improve. And one of the things they talk about here is imitation versus reinforcement learning. So our current approach primarily relies on imitation learning. So what they mean by that is that kind of where the intelligence is coming from in these models is from these data sets, right? So like fundamentally what you're doing is you're collecting a bunch of humans that are teleoping these robots, and then you're using a deep learning model to try to imitate those humans, right? So like the intelligence is fundamentally a kind of like an imitative kind of intelligence where you're imitating the humans, right? Which is actually very similar to early language models, right? Early language models, that's really what they were, like GPT-3, right? Like there's no RL on that, right? But maybe there's RLHF, but the majority of the intelligence in these earlier language models is basically they're trying to imitate humans on Reddit. They're trying to imitate Wikipedia text, right? So robotics is still at that point where we're kind of doing this imitation learning, and we're not yet at reinforcement learning, but that is going to be a huge part of it, right? And there is a lot of reinforcement learning in robotics. I've done reinforcement learning for robotics, but that's not the same thing, right? the reinforcement learning that people do in robotics now is almost like a 2015 type of reinforcement learning, right? It's like you have a little tiny multi-layer perceptron, and you're like it's not the same thing, right? It's not the same thing as like GRPO and these kind of more intense RL frameworks that people are coming up with for modern AIs versus kind of like the old school classic little tiny MLP reinforcement learning that you would see in robotics all the time. So here's a couple slides from one of the OpenAI talks, and they talk about scaling reinforcement learning. So the amount of pre-training compute, right, which is this kind of like imitation learning, kind of like here's a bunch of human data, just try to match this human data compared to the RL compute. And then what does it look like when we scale that, right? When the pre-training compute is just a tiny fraction of the total RL compute. And then this picture here, this is a reference to the Jan LeCun cherry on top, but it's a pretty old reference. So Jan LeCun had a famous slide where he talked about how pre-training was going to be a small part of it. I think in his slide, he actually was using self-supervised learning, supervised learning, and then RL, but now we kind of bucket it differently. We use different terminology. We call it pre-training versus RL. And yeah, I think it's going to be like this, right? And we're not at this point in robotics. We're barely getting here. We're like starting to get into this point with language models, right? Where some of the latest language models, reinforcement learning is a big part of the story, right? Especially with things like math and code, right? You're using a lot of RL compute. With robotics, it's not at all the case yet, right? So we're going to get there with robotics, and we're starting to see the kind of beginnings of the frameworks that we could use for that, right? So TRL from Hugging Face, Prime Intellect has been making a lot of splash recently with their Prime RL. They have their own kind of RL framework. I don't know, like these still feel kind of clunky. I still feel like there's going to be a reinforcement learning framework specifically for robots that Hugging Face releases. I don't have any secret insider knowledge. I don't know anything that they're doing, but I would bet you money that they're working on something that integrates kind of better with the robot data sets. And generally when you're talking about reinforcement learning and robotics, you're talking about simulation, right? So the reinforcement learning is happening in simulation, but now that we have, as we were talking about before, this concept that, hey, even if you're doing reinforcement learning in simulation, you can still get feedback from a VLM and use a VLM as a kind of a reward signal. So some combination of reinforcement learning with vision language models as feedback in simulation for robotics, I think that put those four things together in a pot and swirl it around, and I think that's the secret recipe for fully general purpose robots. And here's another thing. Okay, so we talked about the model capacity is still not quite there for robots. We're still not really using reinforcement learning, and we still haven't even gotten into reasoning models, right? So there was this whole kind of like explosion recently about reasoning models and test time compute, right? Where, hey, if you're trying to solve some problem, if you actually let your model kind of produce a bunch of tokens and then use those tokens to kind of think more about the problem, then you get a better answer, right? So as you increase kind of the amount of thinking tokens, right? So like if you go back up to our little image here, right, think about this, right? So the vision language model is producing these tokens here and these tokens here. What if this vision language model was given kind of a reasoning budget, right? So we could actually produce many, many, many more tokens, and then those tokens would be given to the action expert, right? So that's something that I haven't really seen at all yet, is the use of kind of test time compute within robotics. And you could see how there's a reason it hasn't really been done before, and part of it is because of this whole inference kind of situation, right? Where like robots need to be reactive, they need to be kind of real time. So this reasoning and thinking and having to sit there and wait for a bunch of tokens to come out, probably not a good fit for a robot that needs to kind of execute actions quickly. But I feel like it's one of the scaling dimensions, and there's no reason to not pursue it. So I feel like we're going to start seeing that, right? We're going to start seeing some kind of reasoning. Maybe there's even like a third level, right? So here, Figure talks about the fast reactive control of system 1, the slower system 2. Maybe there's going to be a system 3, which is an even slower loop, right? An even slower kind of thinking model that has like, that's operating like it's sending something every minute, right? So this is happening at 10 hertz. the fast reactive control is happening at 20 hertz. Maybe you have something that's happening at like 0.1 hertz, which is like this like reasoning model that's actually thinking more deeply about like, hey, what should I be doing today, right? Like maybe when the robot comes into the factory or something. All right. And that's basically the paper, guys. I do want to point out one thing, which I thought was really cool, is this section here. It's not something you see every day on a paper, but Hugging Face was literally in the appendix list of data sets. It's 4 pages of just here is every single data set that we used, which I think is beautiful, right? It's like there's so many papers where you guys have heard me complain about the data set being completely obscure, right? Like there's no information. Where did you get this data? And the reason people do that is because, hey, maybe they're training on YouTube. They don't want to tell you they're training on YouTube, right? There's like legal kind of gray areas where it's sketchy for them to tell you that they're training on stuff. So nobody wants to include information on the data set in their paper, but I'm very glad that Hugging Face was like, no, fuck that. Here's every single data set that we used. If you want to look at it and you want to Control F and try to find your name and see if your name is on there, you can do that. And I think that's a very good precedent to set of just, hey, just if you're going to be releasing these foundation models and if you're going to claim open source, tell me what data you trained on, because that is effectively what the model is. The model is just a model of the data. So post your data set, put the nutrition facts on there. All right, we got some questions here. My student is going to start uni in a few months. What advice can I give him when it comes to pursuing robotics? I don't know, to be honest. I feel like robotics, the good thing about robots is that there's so many different things that have to come together for a robot that you can work on all kinds of different things, right? So there's obviously the whole model part, but you could work on the data, you could work on the hardware, right? You can work on the software. Like robotics is like a multifaceted problem where there's like a million different little sub problems that you need to solve. So it's kind of an engineer kind of candy store, right? Where there's a million different problems you can solve. You get to pick the one that appeals to you the most, that kind of complements your skill set the best, and just work on that, you know? And if you don't like focusing on one specific narrow thing, you can also kind of be more broad. And that's kind of what I do, right? I feel like robotics has given me the opportunity to kind of cultivate a broad engineering skill set rather than like a very narrow engineering skill set. And I appreciate that, right? If you're working in a different part of the tech stack, the incentive is to be very, very narrow, right? Become an expert in one specific thing. But with robotics, there is always an incentive to kind of understand the whole system. So you can be a generalist in robotics. It's harder to be a generalist in different fields of machine learning. All right. What do you think about the native avenue of robotics AI versus something like Claude teleoperating robots via tool use? What would you bet on being the eventual industry standard? I mean, that's kind of what's happening already, right? If you think about it, like, what is this, right? This is really just a vision language model, right? Which is, what is this going to look like in the future? Well, this is just going to be whatever the most, like, juiced general purpose model is, and then this is kind of the quote-unquote tool, except in this case, it's, like, glued together, you know? It's like you're taking the intermediate representations, and it's like, it's much more connected, but you can eventually see some separation happening here, and eventually kind of you have kind of the robot is just a tool that's being operated by kind of the most intelligent possible kind of generic model you have. So yeah, that is a potential future, but it really depends on this question right here, right? I think this to me is like the fundamental design question that determines the future of robotics is the model being hosted on the robot, or is the model being hosted in the cloud? If the model is being hosted in the cloud, we're going to see bigger and bigger robot policy, which then kind of incentivizes the robot policy being very, very similar to the models that are already hosted in the cloud for other use cases. And it incentivizes the collection of robot data, right? It means the robot gets cheaper because you don't have to put this edge device on the robot. So that's one possible future. In a different possible future, the a model is running on the robot inside some limited edge device, at which point the model is not going to be the latest Claude model because it needs to fit into this tiny little edge device. So you're going to see probably more like this VLA kind of approach. So the future is still unsure, but it depends on some external factors. The mic volume is good, but do you still have the pop filter? No, I took out the pop filter because I'm not particularly percussive with my voice, but maybe I should add it. There's already a filter on this, but I don't know. You guys tell me. I appreciate the audio feedback. It lets me know how to improve the audio. All right. So let me end with some kind of unrelated closing thoughts here. So actually, one more story. I did train this, right? So I went into the repo and I brought an old reliable, my 3090. You know, I've been training stuff on this little 3090 for years now. And here's the training run. So I just used the default settings that they had, 200,000 steps at a batch size of 64. This is a fine tuning on this SVLA SO100 stacking. You can see here's the NVIDIA SMI for my 3090. Takes about 17 gigs of memory. You can see the power consumption is pretty high. The GPU utilization is pretty high. This is the actual training run. So you can see here, this is the step. So I trained 238,000 steps, and it took about 9 a.m. to about 4 p.m. So I let it run for basically a day. You can see here the learning rate was going down, some kind of learning rate scheduler that they have. And you can see here the loss and then the grad norm. So the grad norm is basically like, what is the magnitude of the gradients that you're pushing? So you can see that it very, very quickly drops down and then becomes very small. So like initially it's training, and you can see here the loss goes down. So it kind of feels like it just went a little bit too long. I feel like I probably could have stopped it here, right? But it worked, you know? Here's the utilization. This was a little concerning here. GPU time spent accessing memory. You see that? So it's spending like half the time accessing memory. Little sketch. This is the GPU temperature was a little bit hot here in Texas, so I had to put this fan and just blast my computer. So this is the computer with the 3090. I was just blasting it with air because it was getting too hot. So, you know, that's how you know stuff is training, when your room just sounds like fans. That I showed. Here's the inference. So I made a little inference script. It's actually right here. So basically what this does is it just loads the model. This is the specific checkpoint that I trained in that fine-tuning. Tokenizer for the task description. Here it makes a dummy image, so 3 images of 512 by 512, a batch size of 1, right, assuming it's just one robot. Puts it into this dictionary and then just sends it into the model, and then you get the sample action. So this produces the action chunk, and then I just do that 100 times, and I see how long is each individual inference step, and then what's the GPU memory that gets used, and you can actually see that right here. It's about 0.2 seconds for inference, so that's basically this time right here. So how long does it take to do the inference? About 0.2 seconds, and it doesn't take a lot of memory, which is good, right? It takes about 2.5 gigs, but there's other stuff there. The Torch like allocates extra GPU memory anyways. The specific GPU memory only for the model is 900 megs, which is very reasonable, right? So it's like 400 million parameters, I think it was. Yeah, 450 M parameters at BS16 kind of equals to roughly 908 megabytes. So tiny, small, reasonable model. I was able to train it on my consumer GPU. I was able to run it on my consumer GPU, so everything checks out there. Sorry, guys, I'm a little bit sick here. All right. I wanted to close out with some thoughts here. So I can see this coming. The DeepSeek moment for robotics foundation models is imminent. So what do I mean by this? So right now, the robotics foundation model space, you have a European company in Hugging Face. You have an American company in NVIDIA. and you have an American company in physical intelligence. I think that there's a big missing country there, which is China. And I think China and one of these robotics companies in China is going to release an open source robot foundation model, right? It might have already happened, and I'm just unaware of it. But if DeepSeek shows that, hey, China can produce very competitive open source models, and if anything, they have a tradition of open source now. They have almost like an incentive to open source. I think that's how they're kind of seeing everything. I think we're going to see Chinese DeepSeek open source robotics foundation model that's probably going to be better than the ones that we have available now. And then we also know that Meta has a whole robotics division. Meta has the kind of legacy of Llama and open source, so they're for sure going to release their own open source robotics foundation model. So I think this time next year, there's probably going to be dozens of different open source robotics foundation models. And this is a good thing, right? So what does this mean for my robotics startup, right? So I'm trying to make this little tattoo robot. What does it mean for me? Well, this is good news because it means I'll never have to spend a ton of money to train from scratch. I will only ever need to fine-tune one of these robotics foundation models on a small data set for my specific embodiment. So if I'm doing a robot that does some little specific thing, and I have my own little custom robot that has a certain amount of degrees of freedom, a certain observation space, certain action space, right? I'm never going to have to train something from scratch, right? I'm never going to have to spend millions of dollars and millions of GPUs to train this giant foundation VLA. I'm just going to be able to go and take whatever the latest VLA is, and there's going to be like a dozen different companies, American companies, European companies, Chinese companies. They're going to be competing with each other to try to create the best possible robot foundation model, and all I'm going to have to do is I'm just going to go pick the best one that exists, fine-tune it on my little specific embodiment, and it's going to be great. And every single year, it's going to get better and better and better and better. So I think this is actually a huge unlock for kind of startups, because it removes this kind of like capital wall that previously existed of like, hey, if you want a good model, you're going to have to spend a ton of money to do it. And I think this kind of vibes with something that Sam Altman said in one of his talks, where you either bet the technology is about as good as it's going to be, or you bet that the technology is going to get massively better. So for robotics, the current foundation models are small and shitty and not particularly good. But I think this time next year, especially when we have Chinese companies entering the race, especially when we get reinforcement learning, especially when we get a couple orders of magnitude in size, especially when we get potentially some kind of reasoning aspect to these robotic foundation models, I think this tech is going to get very, very good. And I think that you're going to be able to fine-tune a robotics foundation model with your little specific embodiment, and it's going to basically give you it's going to animate. It's going to be a way to take the random motors that you have sitting around your house and basically turn them into this living thing, which is going to be pretty crazy, right? So like all those weird robots and servos that are laying around in your house, I think we're about 1 year away from them being able to basically like do any kind of task you can give them. So we're going to end it on that high note, but I'm going to use this. This is Asterix, which is a French comic book, and the Hugging Face team loves to kind of reference it. I think it's because they're very French, you know. So, for example, this one here, Idefix, that's actually the little dog in this, and this is Obelix, right? So, I figured if we're doing a review of Hugging Face paper, we'll end it on a Asterix fin, and that's basically it, guys. SmolVLA, a great addition to open source robotics. And yeah, you can use it. You can fine tune it. Have fun with it. Thank you, Daniel, Z, Aries, 770, Thomas, Zeke, Everydream, Richard, SHZ, Mark, Lil KM, Calentuz, Karan. Thanks everybody for hanging out. I'm going to blow this horn, and we're going to end it there.